Hello and welcome. In this video we'll talk about the conditional mean function, or CMF for short. You may remember that the conditional mean function gives us the average value of a random variable in a subpopulation satisfying certain characteristics. Why is it helpful to really understand the conditional mean function? Well, it will give us three very important insights. First, it will allow us to consider empirical problems where we're not interested in causal inference, but instead want to predict or forecast an economic variable. Second, for causal inference, we relied on an exogeneity or balancing assumption. We will be able to provide an alternative interpretation of this assumption. And third, once we really understand the conditional mean function, it will become obvious how we can use data to estimate. In particular, it will be straightforward for us to derive the OLS estimator for the linear regression model. We'll start by reviewing some fundamental statistics. In particular, we want to consider the problem of predicting a random variable. We want to predict a random variable, let's call it y. To make things more concrete, you can think of y as the test score of a randomly drawn student. We predict y by some number, let's call it a. Timing is important here. Before you draw the test score, I will state a number a, and this number a will be a guess of the test score. When I'm deciding on the number, the uncertainty here is not resolved. We can think of a as something that is fixed, and y something that is random. Before we move on, let's turn this into a proper sentence. We predict the random variable y by a. So I like this much better. Instead of predicting a, we may predict some other number. Let's call it b. And let's choose a special value of b. Let's choose b equal to the expectation of y. Or in other words, we set b equal to the population average of y. Now we want to determine which one of these two numbers is the better prediction. An intuitive criterion for a prediction to be good is that the prediction is close to y, but a is fixed and y is random with some variance. Therefore, it's not possible for a to always be equal to y. We will make prediction errors. The only thing that we can do is to make sure that prediction error, measured in some way, is as small as possible. How can we define a measure of prediction error? We make a prediction error if y and a are not identical. So it's natural to look at the difference between y and a. It's intuitive to define prediction error as a measure of closeness between y and a. Now this difference can take on positive as well as negative values, but closeness should always be positive. We can make sure it is by squaring this difference. Squaring is intuitively desirable also for another reason. Recall that the square function is convex. Now suppose that we measure this distance to be this number. By squaring, we translate this distance to this prediction error. Now if we double the distance, we don't double prediction error. Why is that? Doubling prediction error would mean that we would move from here to here. That is, it would mean that we move along a straight line. But since the square function is convex, we're moving a lot higher than a straight line. Therefore, doubling the distance increases prediction error more than twofold. This makes sense since we're really worried about large deviations, and squaring emphasizes large deviation and plays down small deviations. This is still a random quantity. It gives us a prediction error for every realization of y. We can translate this into an overall measure of prediction error by averaging over all possible y's. This is called the expected prediction error. Let's abbreviate this EPE. The EPE is a number that measures the accuracy of A as a prediction of y. If the EPE is a small number, then y tends to realize close to what we predicted. If the EPE is a large number, then y tends to realize far away from what we predicted. Now that we've defined prediction error for the blue prediction A, we can define it in the same way for the green prediction B. For this, it is important to realize that B is just a number, just like A. Sure, it is a special number, but expectations are numbers. In our example, this expectation is the population average of test score. So clearly a number. Now we can horse race these two predictions. Which one is the better prediction? A prediction is better if it has smaller prediction error. So which one has smaller prediction error? It can be shown that predicting the expectation always gives the smallest prediction error possible. In this sense, the expectation is the best prediction. This result will help us a great deal in understanding the conditional mean function. The conditional mean function m of x is the conditional average of our outcome variable y in a subpopulation defined by x. Think of y as test score and x as class size. This conditional average is called the conditional expectation. In our causal model, this equality arose from the balancing assumption. For what we will be discussing now, it doesn't matter where this equality comes from. In fact, we may just define m to be equal to this conditional mean. Consider the following prediction problem. For a randomly drawn class, we want to predict the average test score at the end of the school year. We know that the best prediction is the average population test score. But this prediction wouldn't exploit the information revealed by the observed class size. So maybe we can improve on this prediction. Let's predict a number that depends on the observed class size. And I write the predicted value as function g of observed x. I want you to think of g as a rule that translates any observed class size to a guess of y. We can compare the general g, which could be anything, to a concrete definition of such a rule, namely our m function. Again, we can compare these two prediction strategies by comparing the expected prediction errors. And to get the EPE for m, we can just copy this and swap out g for m. At this point, you're probably not surprised to hear that the m function gives the best prediction. This here is the best prediction using information in x. This allows us to interpret the conditional population average as an optimal prediction. in the same way that we could interpret the unconditional expectation average as an optimal prediction. There is no contradiction between both of them being optimal. Clearly, m of x depends on the random x and is therefore random itself. M of x is therefore not a valid, fixed numerical value in this framework. This new interpretation of the m function gives us immediately access to these three powerful applications. Let's start with the first one, predicting economic variables. As an example, consider the problem of predicting inflation tomorrow. Suppose that we are on this timeline. Let's call our current period period 0. And the next time period, or tomorrow, is t equal 1. We're interested in an outcome at t equal 1. And this could be inflation. We cannot observe tomorrow's values yet. We can only predict. This is called making a forecast. While we cannot observe tomorrow, we can observe the economy today. Let's suppose that we are observing three indicators, x1, x2, and x3. x1 may be inflation today. So this is domestic inflation. Let's define x2 to be inflation abroad. And for x3, let's choose a monetary policy tool. For example, let's go with the interest rate set by the central bank. In the US, this is called the federal funds rate. We want to aggregate all of these economic variables into a guess of inflation tomorrow. Let's denote the aggregation rule by G. Then our guess will be G of x1, x2, and x3. How should we choose G? Well, if we want the best prediction, then we should obviously opt for M. This shows that the conditional mean function, or CMF, is important when we want to make predictions or forecasts. We'll get back to prediction and forecasting problems later in this course. For now, we move on to point 2, interpreting the exogeneity assumption. We defined an exogeneity assumption for the regression model here. I will copy this expression, but be a little bit more general, so instead of d in x1, I just write x1 and x2. And the implicit understanding is that we can even add x3, x4, and so on without really changing the argument. So it's all about the conditional expectation of u given x1 and x2. And to have an example in mind, you may find it helpful to think of x1 as class size and x2 the PD index. When we were averaging over y, or predicting y, which we now know is equivalent, we call this the m function. Let's call this something different. Let's call it the u function. So what was the exogeneity assumption again? The exogeneity assumption stated that this should always be 0. We can now write this more compactly as requiring that u is 0 for all values lowercase x1 and x2. Now let's apply what we've just learned about the interpretation of the conditional expectation as a best prediction. Let's draw x1 and x2, and based on the observed x1 and x2, we predict u. For example, suppose that we draw 30 and 20. What u do we predict? Well, if the exogeneity assumption holds, then we can plug in these numbers here and get the best prediction on the right hand side, and it's 0. Let's make another draw. Suppose we draw 24 and 5. What do we predict for u? Well, again, we can plug in and we'll get a 0. And now you may already see where this is going. Regardless of what we're drawing, we will always predict a 0, so we will always predict the same number. So it doesn't matter at all what x1 and x2 we draw. Our prediction will just ignore this information. But our predictions were based on u, which is the best prediction rule, so it is optimal to ignore the values of x1 and x2. But if that's the case, then x1 and x2 are useless for predicting u. Or in other words, u cannot be predicted from x1 and x2. To me, this is a really helpful rephrasing of the exogeneity assumption. Let's apply it to our example. We've already specified what x1 and x2 are, but what is u? Well, u is the total effect of all other factors that affect test scores. For now, think of it as teacher quality. Let's apply this interpretation of the exogeneity assumption. Class size and PD index are not allowed to predict the effect that teacher quality has on test scores. This makes it easy to see that the exogeneity assumption is unlikely to be satisfied if the highest quality teachers teach in districts where the PD index is low or where there are few disadvantaged students, or if the best teachers tend to teach in the smallest classes. From this version of the exogeneity assumption, it's also easy to derive a necessary condition for exogeneity. That is a condition that has to hold, or else exogeneity cannot hold. Let's talk about correlations. We consider the joint distribution of x1 and u. Suppose that we are able to draw samples from this joint distribution. And suppose that a typical sample looks like this. What comes to mind when you see this distribution? Yes, exactly. U and x1 are probably positively correlated. Now suppose that you only observe x1, but not u, and you want to use the information x1 to predict u. Suppose first that you observe a small value of x1, maybe this one. Let's call it x1 underbar. For small x, u tends to be rather small, so you would probably predict a small u, maybe this value. Similarly, if you observe a large value of x1, x1 bar, you expect the u to be rather large, and you would predict a larger value of u, maybe this value. This shows that the conditional expectation of u at the small x value has to be smaller than the corresponding conditional expectation at the larger x1 value. Now wait, this looks very different from what we had under exogeneity. That's right, under exogeneity we always predicted the same value, regardless of the value of the regressors. But now we predict different values for different values of the regressor. Therefore, if u and x1 are positively correlated, exogeneity cannot hold. We can argue in exactly the same way for negative correlations. Therefore, under exogeneity, u and x1 cannot be negatively correlated. That leaves only one possibility. U and x1 have to be uncorrelated. If exogeneity holds, then u and x1 have to be uncorrelated. By symmetry, this means of course that u and x2 also have to be uncorrelated. Sometimes it's fairly easy to argue that a regressor and the error term are correlated. This is enough to show that the exogeneity assumption fails. Now let's move on to the last point on our agenda: estimation of conditional mean functions. We already know that the conditional mean function m minimizes prediction error. Here the minimization is over all candidate functions gray m. So to find the conditional mean function, all we have to do is look at all possible m's, feed them into this criterion, compute the expected prediction error, and then in the end pick the m that gave the smallest expected prediction error. Now you may worry about how to do this computationally. After all, there are a lot of possible functions to look at. But there's an even bigger problem. We cannot compute this expectation because we don't know what the population distribution of these variables is. But the method of moments comes to the rescue. We can estimate m by emulating this optimization problem in the sample. We just replace the population distribution by the sample distribution. Obviously, we may now not get m. We get something that's data dependent and that is an estimator of m. Let's indicate this by a hat. M hat defined in this way is called a least squares estimator. Now it's time for us to worry about computational issues. This optimization problem is well defined. We have everything to compute this criterion for every choice of m, but there are so many possible m to look at. Fortunately, this becomes a lot easier once we look at the linear regression model. For the linear regression model, we can just copy this estimation strategy. In linear regression, the m functions that we have to look at have a particular shape. They are linear, hence the name. Let's plug this shape in. Now it's obvious that to search over all suitable m functions, we just have to search over coefficients beta 0, beta 1, and beta 2. Fortunately, this is an optimization problem that is very easy to solve. The estimated m function now corresponds to estimated coefficients. Let's call them beta hats. These estimated coefficients are called the ordinary least squares estimator, or just OLS. The definition of the estimator may still seem a little vague. We will clarify it in a simple example. But then again, I don't want you to worry too much about the details. Here I just wanted to give you some intuition of how the estimation works. Since the estimation routines are implemented in statistical software, such as Stata, you never have to carry out the estimation yourself. And to apply econometric methods, it's not really important at all to understand how the OLS estimator is implemented. The very last thing that I want to discuss in this video is a very subtle issue. In this minimization problem, we found m by finding the m that minimizes this criterion. The implicit assumption was that there's only one such m that is optimal, and in some way that is actually true. This definition worked really well for the m function. It continues to work in the linear regression model, but it doesn't have to work for the coefficients. Now this may seem surprising, because if we have a unique m function, then in the linear regression model we should have unique coefficients, right? Not quite. Let's look at an example. Suppose that these are all the classrooms in our population. Let's split our population in half. In the orange half, classroom size is less or equal to 25. In the blue half, class size is larger than 25. Let's suppose that the average score in the blue subpopulation is 73, and the corresponding average in the other subpopulation is 71. Now let's define two binary variables. b1 is equal to 1 if x1 is smaller than 25, and 0 otherwise. For b2, we exactly reverse this definition. Note that b1 and b2 are different ways of encoding in what subpopulation we are. Now suppose that we make b1 and b2 our regressors. The conditional mean function m is a function of b1 and b2. We know that m has to spit out 71 if b1 and b2 indicate that we are in this subpopulation. Otherwise, it has to return 73. One way to accomplish this is to define the following coefficients. An intercept of 71, first slope coefficient equal to 0, and the other slope coefficient equal to 2. But that's not the only way. We can also write or in fact, there are many more ways. As you can see, while it is clear what the m function should be, it's not clear what coefficients we should choose to get that m function. The underlying problem is, of course, that b1 and b2 encode the same information. We are using too many binary variables. Since binary variables are also called dummy variables, this is called the dummy variable trap. The dummy variable trap and other related issues are ruled out by the full rank assumption. Sometimes this assumption is also called the assumption of no perfect co-linearity. The exact definition of the full rank assumption is quite technical, and also it's not an assumption that you typically have to worry about. Therefore, I won't discuss it in detail in this course. Even if you accidentally specify a linear regression model that violates the full rank assumption, it's typically not a problem. Regression software, such as Stata, will tell you that you made a mistake. Let me demonstrate. Here I am in Stata, and I've already loaded our classroom data. Let's code up the b1 and b2 variables. Let's check if this worked. And this is looking very good. b1 is 1 for the small classrooms, and b2 is 1 for the larger classrooms. Now let's run a regression. Let's regress test score on b1 and b2. And we can see that Stata realized that there was an issue. It detects co-linearity, so it detects a failure of the full rank assumption, and it automatically drops one of the two dummies. When you run into this issue yourself, typically you wouldn't leave it at that, but you would go back to your specification and think about why this is happening, and then you would manually drop a variable from your specification and run this, hopefully without this happening again. Learning more about the conditional mean function has taken us on a journey through surprisingly different topics. That's it for this video. Thanks for watching.